There we
Thank
go.
you.
Yes, sir. So that's the dead giveaway. Okay, and then so it wants to know, find the probability that more than 8 cars arrive at an intersection. So the probability that more than 8. Okay, that's what I'm looking for. Yeah, I can't find that because it goes to infinity. Are you with me? It goes forever. Now, I will say this, that if you did this out to, like, if you let x equal, for instance, 100, for all intents and purposes, f of 100 is, for all intents and purposes, 0. Oops, I don't know why I put 2 zeros. It's 0. Oh, that reminds me. So I'm on a video call the other day, Zoom meeting, whatever, with our high school staff, and I will write a book one of these days about things that my bosses have said over the years. I'm just like, what did you say? So her direct quote of the day was, make sure you don't put a super 0 in the grade book. I'm sorry, what now? And this is something that's been in education for some years now. I used to get in a fight about it. Now I just don't really care that much, except that I about snapped yesterday because I couldn't deal with it anymore. But finally just said, no, let it go, just let it go. The idea that if a kid doesn't do anything, you give them a 0, see, then they don't feel like doing anything. And that just punishes them by putting a 0 in. And I got in an argument with my old boss. I said, oh, you mean the computer just does math with the numbers? It actually takes the 0, which is a thing, and it factors it in, and that's what you got on the assignment. And so what they're thinking now is they'd like you to put in like half credit, 50% or more in the grade book, whether they did it or not. See, that way when they're failing, they don't feel so bad about themselves. Anyway, this is why I hate teaching high school, and I like being in the college section a lot of times. I rarely have to deal with ridiculousness, or if I do, I just hit delete in my PCC email, for instance. So, but once in a while, you just look at stuff and you're like, sorry, what did you say? Super 0. So this is about 0, I will guarantee you. Okay, it's as close to 0 as you'll ever want to get, meaning that from 100 to infinity, it's just you're adding a bunch of zeros in essence. Okay. That said, this is too hard to find. So what I'm going to do is I'm going to use the trick that I showed you, that this plus this is equal to 100%. Okay? And we're going to do a little bit of algebra. And then we're going to solve this problem. Okay? And so this is, that's how we're going to go about doing this. Now, I'm going to use Excel to crunch this out because I just don't want to do this by hand, or I could do it on my calculator. I think I'm just going to prefer Excel. So I'm going to bring that up, and I will share that with you momentarily. Share screen, Excel, open. Cool. Somewhere. Get bigger, get bigger. So when I do something like this, and I do it in Excel, what I like to do is, can you see that, or did it stop sharing? Oh, it didn't stop sharing, didn't it? Why? Oh, wait, why did it do that?
I can see your Excel like homepage. There you go.
All right. So what I like to do is I like to do X and then f of X, just to help me keep track of what I'm doing. I don't really care other than that. So we know that we're interested in 0, 1. Oh, for Pete's sakes, touch screens are fun. 0, 1, 2, 3, 4, 5, 6, 7, and 8. Okay. And then my function is equals exp of -6. That's e to the -6 in Excel lingo, times 6 to the x divided by, and then fact of this guy. Okay. So this would be the probability of no cars showing up. And there we have it down to there. So the probability that it's less than or equal to 8 is just the sum of those guys. So that's about 84%. So if you come back to your, stop sharing, start sharing. If you come back to this guy, the one we had is 84% roughly. And so the one I want then is roughly 16%. So That's how I'd go about finding that. Okay. The big trick is looking at this guy right here. It said greater than 8. So the tricky part is always, do I include 8 or do I not include 8? Well, they didn't include 8, so I will include 8 in my other format. If they had asked for the probability that x is greater than or equal to 8, then I would have started off with, well, that's equal to this guy. This I don't really have because there's nothing less than 8 until you get down to 7. So this is the exact same thing as saying this plus this, because there is no 7.5. And they're here. Then I would just take and subtract this guy to the other side. Okay. And functionally on Excel, where am I at? No, it's too many screens. Stop it. If functionally in Excel, then all you would do is sum one. Why did it pause? Oh, there it goes. You just sum one fewer numbers. So that would be 74%, meaning that the number that I'm interested in is 1 minus that. So basically 26%.
Okay, that makes sense.
Okay. And then part B or whatever says probably only 2 cars arrive. Well, only 2 is right there, right?
Right.
Mm-hmm.
Yep, got it.
So keep in mind, you could keep this thing going forever. And you will see that, yeah, E minus 13, E minus whatever, E minus 30. I'm surprised that Betsy hasn't told us to take a flying leap yet, but we'll keep going. Pretty soon she's just going to say, screw you, it's 0. Even though it's not truly 0, it's basically 0. And so, 31 zeros in front of our number. Oh, come on. Don't make a liar out of me, Betsy. Didn't I say 100? I said 100 was basically 0. I'll go to 200. Cool. Come on. Come on. There we go. And at some point, oh, okay. You're just showing off Excel. Oh, there you go. Yeah, see right there? 173. Screw you, I'm not doing it. Okay, it's 0. Okay. And the reason it's not doing it is because it can't find 171 factorial. That's just way too big a number to do, and it just punts at that point.
All right, thank you.
Yep. Anybody else got a question you want to see, or jump in? Feel free, jump in. Anybody feel okay with the homework? I haven't heard any complaints yet. To my face, anyway. No? All right. Well, you can think of another one while I do want to talk about something here. Screen share. Sure, let's do that. And get one of those and some of this action. Okay. Now, I'm going to just make up a random problem. Let's just say f of x and y. F of x and y is equal to, and I'm going to do this because I'm too lazy to look one up in the book or whatever. There we go. And I'm going to define an interval that is defined on because I can. And I'm going to tell you that this is a joint PDF. Joint meaning that together they follow this formulation. We know that the double integral of this guy from 0 to 1 and 0 to 2. Okay, now look, remember we're integrating over a rectangle in the xy plane. So the volume under this guy over this rectangle needs to be 1. Notice it cannot be negative. You cannot have any negative z values, none, because that would equate to a negative probability. That can't happen. And we cannot have it integrate to more than 100%. That'd also be a problem. So let's just double check this. Now I know this will work because, well, I cheated, of course, and put this a in front of it. I can make it work. So it's going to be x cubed over 3 times y from 0 to 1. So that's it's going to bring that 1/3 out front. And then that's going to be a over 3 times y squared over 2, 0 to 2. It's going to be 4 halves, which is 2, minus 0, so it's 2. So you're going to have 2/3 a is equal to 1. So a would be 3 halves. Nice. So coming back up here, this guy here is my joint PDF. Okay. Again, the rules are must integrate to 1, can never have any negative values for z in this guy. I mean, that's our z equals, right? There cannot be any negatives. That would imply a negative probability. And it has to sum up to 1. You have to have 100%. So if I said to you, hey, what is the marginal with respect to x? Well, what I'm going to do is I'm going to integrate over the y's. I'm going to get rid of my y's, and all I'll have left is x's. So if I do that, I will get, that's x, I just leave the 3 halves in the x squared because they're operating as constants right now. So if you plug that in, you get 4 over 2, which is 2, times this is going to be 3x squared, I believe. Nice. And if you wanted f sub y, you'd integrate over the x's. So 3 halves, again, the y just hangs out, and this is going to be x cubed over 3, 0 to 1. And you will get 1/3. So you're going to get 1/2 of a y, I guess. Oh, that's hot. That's nice. That's awesome. And so look what happens. What happens if you take f of x times f of y? Well, you would get 3x squared times 1/2 y, aka 3 halves x squared y. Nice. And what does that represent to us? That means that in this problem, x and y are independent. That is, if and only if f of f, the marginal of x times the marginal of y is equal to the joint PDF, then they are independent. Now, that's an if and only if situation. So in this case, we showed that it's true. Bam, they're independent. If I tell you they're independent, then you know this is a true statement. Okay, that concept is not very hard to do. Integrate with if you want the marginal of x, integrate with respect to y. If you want the marginal of y, integrate with respect to x. It's easy. Remember, you want to have the variable that you want, the marginal of x. I want to have x's left over. Well, that means I got to get rid of the y's. How do you get rid of y's? You integrate with respect. Okay. And then a joint PDF, let's say the probability that, I don't know, probability that y, where are we at up here? Oh yeah, probability that y is less than 1, given that x is equal to 3. Okay, well, that's interesting. Remember, what that means is I'm going to take this guy, I'm going to divide out by this guy because he's the one that is given, okay, but it's f sub x evaluated in this case at 3, okay. Also, this guy evaluated at 3. Meaning that when I go to do this problem, all I'm going to have is a function of y on top over some constant on the bottom. So if a person goes, well, how am I going to integrate this thing? Well, you're going to integrate, in this case, with respect to y, because it's what we're asking about up here. We're going to go from 0 to 1. And we're going to go from 0 to 1. It's the only way it can happen. We cannot integrate, oops, sorry about that. We cannot integrate with respect to x because we're saying we're letting x equal a particular value. So if I were to do this problem, remember our original problem was 3 halves x squared y over Now what's our marginal with respect to x? Well, it's 3x squared. Okay, and then we're going to integrate this sucker from 0 to 1 dy. But if you're smart, you're like, oh, well, cancel, 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 cancel. Well, that's hot. What am I left with? 1/2 y dy. Wait a minute, isn't that just the marginal? Exactly, that's right. It is exactly the marginal if they're independent. If they weren't independent, that wouldn't be true. Okay, and so you plug this baby in, you get 1 squared over 2 times 1/2 from 0 to 1. It's going to be 1/4. About 25% chance that it's less than or equal to 1. Less than or equal to or less than. Remember, with a discrete distribution, it matters not whether it's equal or not. Its only difference is, are we counting that endpoint or not? But the idea on an integral, remember, is if you're integrating this thing, this function from A to B, it's finding the area. Well, whether I include B or not include B doesn't make any difference, because how much area does that line have? Nada, a big fat goose egg. So it makes no difference at all in terms of my integration. Okay. Now, of course, if your endpoint went to infinity because there was a asymptote there, you'd have a bigger fish to fry, pal, because that ain't a PDF. Okay. Because remember, it has to integrate to 1. And if it goes to infinity, like positive infinity, like, yeah, that's going to be an issue. Okay. So good news is that'll never happen on a PDF. So meaning that our endpoints, whether I include them or not, makes no difference, because again, there they go. That is kind of a big concept. When they are multiplied like this, and you're integrating over a rectangle, like, take it to the bank, they're going to be independent. Okay. However, if a person had something like this guy, oh, I'm sorry, I didn't ask for questions. I'll stop and ask for questions. Anybody have any questions on that one before I go on? No? All right. Oh, I gotta be careful. I am going to look this up on the 3D calc plotter. I'll do it on the other computer though. That one's too hard to type on. And so, yes, stop screen sharing. We don't care about you. Oh, someone want, oh, for God's sakes, yes. Email me all the time, you weirdos. All right, now here we go. Calc plot 3D. There she blows. So what I want is I'm going to look at that function in a 3D calc plotter, and I just want to make sure that it sits above the XY plane. That's all I care about. Oh, in the region that I'm interested in. Oh, crap. I shared the screen with you, and now I can't see my... What just happened? Okay, there you go. Crap, I can't see anything on this one. Well, too bad. I have to do this first. I'll do this. I'll type it back in here, and we'll come back to you. Come on, share it with me. There you go. Sorry. Oh, now I can't. Oh, for God's sakes. I'm going to write this on a sheet of paper. I'll write it on my knee if I have to. All right. X squared y. That pen will not write on paper. X squared y plus y squared plus 5. Okay, got it. Gracious. Trust me, folks. I know what I'm doing. All right. Share. Yes. There we go. So, system blank. Okay, so yeah, I don't care about you, sir. X squared times y plus y squared plus 5. Okay, feel pretty good about that. Everything's above the z axis, above the xy plane, or the z equals 0 plane. So feel pretty good about that. So I'm going to run with this equation. I am going to make up an area or a region to integrate it over, and we'll just make it work. Again, kind of like we did on the last one. I just find it to be, good Lord. I find that to just be a little easier way of going about it. So I'm just going to say, let's just let x go from 0 to 1, sure. and we'll put a big A in front of this whole mess, and we'll just make it work. And let's let y go somewhere between here and yes, 1 minus x, a very boring problem. Cool. Now the fact that y is bounded by a function of x pretty much screams to me that they are not independent, because obviously y depends on what x is. Okay, we're looking at this region in here. Okay, we could just as easily flip this around and do 0 less than y less than 1, and we could do 0 less than x, or sorry, less than, yes, less than x, less than, what is that, y minus 1, 1 minus y. It's 1 minus y as well, isn't it? Correct. Because, right, when x is 0, y is 1. Right, yeah, that's right. Nice. So it doesn't matter. You don't have to write that way. Just be aware that there he goes. Also, there's addition. Addition screams that it's probably not going to be independent, because you remember you have to write it as a product. It's not 100% guarantee, because Mr. Groom could get fancy and try to fool you, which is not something I don't do that a lot, but once in a while, it's kind of fun to do. Maybe the function could be factored, and then, oh, there, I could write like that, and then I would end up with an independent situation. Okay, it's too late in the day to integrate this by hand, so I'm not going to try. Here, escape, stupid, escape. F3, integrate, F3, integrate. And by all means, when you do these, by all means, knock yourself out. Use a calculator of any kind to do the integrations. I assume that if you needed to, you could probably pull it off. It's just, we've got better things to do. (13/5). So what I have then is 13/5. A is equal to 1, because it has to equal 1. So A is 5/13. Okay. So I'm going to rewrite that down here. Like so. And then if you want to find the marginal with respect to x, all you're going to do is, all right, cool, let's get rid of this stuff. So 5/13 x squared y squared plus 5. And again, I need to get rid of the y's to get functions of x. So here, so I'm going to integrate with respect to y. And y goes from 0 to 1 minus x. Wait, you're like, wait, didn't we already have this up here? Yeah, kind of. So if you get rid of that outer integral, and you replace that with a 5/13, like so, there you have it. It's that grossness. 5 x minus 1, gross. 3x cubed minus 5x squared. No, it won't be this one that's gross on the test. Plus 4x minus 32. All over 78. Now, if I was a betting man, I'm going to say it. I don't really care what f of y is. I'm going to take all the money I have and I will ever make and say that f of x times f of y will not equal this thing. I mean, look at this hairy mess. So because that, it says to me these guys are dependent, which again, I pretty much knew that going in based on how the y depended on the x for its limits of integration, and because there was addition instead of multiplication. Okay. So as I do this one here, now you're like, oh wait, I got to get rid of the x's. How am I going to get rid of the x's, Jay? Because the x's go from 0 to 1. And so you're like, well, yeah, they go from 0 to 1. That's right. 0 to 1. So in this case, f of y is equal to 5/13. Okay. And then, oh, well, I shouldn't do that. Let's do this hard part here. So down here again, all I'm going to do this time, you see, All right, the 5/13. Here's my single integral. The difference this time, I'm going to integrate with respect to x from 0 to 1. And I get that. So 5 y squared, no, 3y squared, sorry. Plus y plus 15 over 39. So once again, this times this does not equal that. And because they don't equal, we say these guys are not independent. They're dependent functions. Okay. Now, I could ask the exact same question on the last one, or something very similar to it. What's the probability that y is less than 0.5, for instance, given that x is equal to 0.5? I don't know. But I do know this, that I have on top, I'm going to have that 5/13 x squared plus y plus y squared plus 5 over, now I need the function of x. I should have done the function of y, it'd have been easier, but whatever. Gross. Again, remember this denominator is a constant. Okay, as soon as I get done here in a minute, it's going to be a constant. So I'm just going to take my calculator, and I have that function somewhere. I'm going to go up and grab it. It's right here. If you've never used it, the pipe button here, which is right next to the 7, if you hit such that x equals 0.5, diamond, enter, yep, 0.9895, yada, yada, yada. Okay, that's my denominator. Nice. And then if I put 0.5 into that numerator, this is what's going to end up with it here. So that numerator is the original function. So I'm just going to type it over again. So 5 divided by 13 integral x squared times y plus y squared plus 5. Okay. I'm going to go ahead and do such that x equals 0.5. Oh, except be careful. Don't do that just yet. I'm going to get rid of that. I'm going to get rid of the integral just for a second. And I'm going to get a value for that guy. So there it is. So really what I'm going to be doing is integrating that function divided by 0.8989 up there. So I'm going to integrate this function with respect to y from, and then where are we going from here? Well, we're going from 0 to 0.5. And so where are you? 0 to 0.5. And then divided by this fella. Cross your fingers. Interesting. 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 So I made a little boo-boo apparently. Interesting. I'll have to chase that down in a second. So let's see what I did wrong. 0.5, 0.5, 0.5. Mm-hmm. No, no. Yep. Okay, makes sense. Okay. All right. So yes, I think we got that down. Let's think about it for a minute. So given that given that x equals 0.5, what's the probability that y is less than or equal to 0.5? Now think about that for a minute. If x is 0.5, we are here somewhere. You with me? That's where we are. Okay. Now we know that our y's must be less than or equal to the line 1 minus x. Well, 1 minus 0.5 is what? 0.5. What is that saying to me? That is saying to me what is the biggest that y could ever be is 0.5. Cool. So what did I just find? I found that there's a 100% chance that I'll be less than 0.5 when that was the maximum that Y could have taken on in that particular interval that I restricted it to. That wasn't a great problem. I apologize. But, there you go. So sometimes you solve and you find that, 5 equals 5. That's kind of neat. So here we have a situation where based on the limits of integration that we gave you initially, when it was all said and done, I kind of freaked myself out because 100%, what the heck? But because of how it was restricted, that's where Y has to be. And because it has to be there, 100% chance. That's all there is. Okay? That one's a little weird. I don't really like it as well, but yeah, it is what it is, I guess. Any questions on those? Again, the process is the exact same every time. On these problems, they will give you a joint distribution. They will typically ask you for both marginals, and then the throwaway question is, are they independent? Again, it's a pretty dead giveaway if they're not integrating over a rectangle, that is, that Y is bounded by a function of X or vice versa. It's almost 100% that they are going to be independent. I would say it's 100%, but I'm sure there's some weird thing out there I never thought about. And also, if your joint distribution has addition and subtraction in it, it's a pretty good bet that it's not independent. One weird example of this, I've done this to people in the past. Or written it like this. People are like, well, of course it's not independent. There's a subtraction. Ooh, not so fast, friend. This can be written like this. And it's quite possible that you could get a marginal of X that looks like that and a marginal of Y that looks like that. And if they did, yay, it works. They're independent. Okay. Question? Feels really weird. I think everyone went to sleep on me. No?
It's one of those things where there's so much that we don't know what to ask or how to phrase the question.
Gotcha. Yeah, after you play with it, I think you'll see it. But just kind of go back and look at the videos and you'll be like, oh, okay, yeah. I think once you see it, once you do a few of them, you're like, oh, that makes sense. But there will never be a time in my life, I don't think, when I'll ever do one of these and get some bizarre answer. Like in this case, it's seemingly bizarre answer of 1. Well, first of all, if it's 1.2, you screwed up. Okay, has to be less than or equal to 100%. But the fact that it came out 100% kind of weirded me out, and I'm actually really glad I almost rounded off to 0.989. Had I done that, I would have ended up with over 100%, which really would have weirded me out. Or had I rounded it up just a little bit, like 0.986 or something, then I would have got like 0.99, and I would have walked away from that going, I'd probably buy that, instead of actually getting the 100% that I wanted. Because if the 100% that's the actual 100% makes me happy, because I go back and I check and oh yeah, that's exactly how we bounded it. That's what it had to come out to look like. Another one that I just want to kind of just beat to death a little bit more, and that's the idea of the CDF. Okay, this thing is always the probability that X is less than or equal to X. Okay, different books will write little x less than or equal to big X. Some will write big X less than little x. I don't really care how you write it. It doesn't make any difference. What we're saying is this: you've got, and specifically in the case of a continuous distribution, although there are CDFs for discretes as well, and we'll do both. What it's saying to us is, you want to know something like, hey, what's the probability that X is less than or equal to 7? Cool. We're going to use the CDF to find that. And then once I have that information, then I can swing it around. And then if I need to do that problem that Bobby was doing earlier, I need to find this guy. Cool. Well, in the case of a continuous distribution, I wouldn't do X less than 7. I would do this guy. Because if you think about it, this guy, this can happen. I can have 7.99999 because it's a continuous distribution. I cannot have 7.99 cars show up at the intersection because that's discrete. They have to come in whole numbers. I can have 7.999 whatever, pounds of trail mix at Winco bulk foods. I don't, whatever. There's lots of things in life that are continuous like that. Give me a better scale. I'll tell you how much I weigh down to the nanogram. And then you're like, well, I get a better scale. Cool. Good for you. Neat. But again, this process will be the same. If I want to solve for this guy, I'm going to minus this guy over here. something to think about is the fact that it's always less than or equal to, okay? That will be a big deal when we get into discrete distributions, because whether it equals 8 or it's less than 8 is a difference, right? And so we'll do one here. Let's just say that this f of x is equal to, I don't know, 2x plus 1 on the interval from I'm tired of using 0, 1 to 4. Look at me be a rebel. Nice. And so if this were true, I know this thing has to integrate to 100% over that interval. And so it's going to be x squared plus x, 1 to 4, times the whole shooting match by a. It's going to be 16 plus 4 is 20, minus 1 plus 1 is 2. So 18a is equal to 1/18. So that means my PDF is really this guy. So what the book will typically write it as is, f of x is equal to 0 elsewhere. And from 1 to 4, this function describes the probability. In fact, if you were to integrate this guy, if you were to integrate this function, it would integrate to 1. That's because in reality, it'd be the integral of 0 from -infinity to 1 plus the integral from 1 to 4 of this guy plus the integral from 4 to infinity of 0. Well, these guys are 0 and this is 1, so yay, it works. Okay, so if we were to look at this guy, this is our PDF, we say. Our CDF would be the integral from 1 to x of 2t plus 1 dt. Now, I don't care what variable you use here and here, but this is the only time I get particularly anal about this. You may not have the same variable down here that you're integrating with respect to and have it show up in the limits of integration. When it's done, I want this CDF to be some function of x. And we typically write PDF as little f of x and CDF as cap f of x, given that the integral of the little f is big F. And that's how we always write it in Calc 2. So here we go. So this would be 1/18 t squared plus t from 1 to x. So you'd end up with 1/18 x squared plus x minus, and plug a 1 in there, minus 2. This thing right here is my CDF. It is a function of x. Okay. Let's look at Desmos real quick, just so you can see it, be comfortable with it. Oh, what did I mess up? Oh, I didn't mess anything up. Just, oh yeah, I did there. Hang on. Yeah, I know. I gotta unfreeze myself. Hang on, I'm looking at something. Something looks a little weird here. Oh no. Interesting. Interesting. Something's a little screwy there, friends. Oops, 2x plus 1. Okay, so there's my Desmos. And remember, we're doing this from 1 to 4. Oops, what just happened? What are you doing? X equals 4. Nice. So we're doing that integral from there to there. Can anybody see anything wrong with my CDF, that red line? It's negative. That's going to be an issue for us, friends. So let's go back and look at my math. And let's see what I did wrong. Anybody see it? So 1/18, that's t squared plus t from 1 to x. You see what I messed up? Can anybody see what I did wrong? Oh, for heaven's sakes, you idiot. No, 16 plus 20. 16 plus 4 is 20. Minus 2 is 18, so that's right. It's time to ask Betsy. Apparently I can't integrate anymore either. 2x plus x, comma x, comma 1, comma 4. Oh, for the love of Pete. Well, it'd be helpful if I could integrate, I guess. That makes sense. So what on earth did I do wrong? Oh, I know what I did wrong. No, it's 2x plus 1. Never mind. I can't even add a calculator now. 2x plus 1. 18. Oh, all right. Anybody have a good comment on what I did wrong? Robert Bosch. Oh, you don't feel bad? I don't feel terrible. I just feel weird. It makes me feel weird more than anything else. Okay, so it's 18. Nice. All right, so that integrates. So then if I do 1/18, put a 1/18 in front of that. Integrates to 1. Awesome. So let's see if I do this. I'm just playing around here. Hang on, I'll be right back with you. Feel weird. Yes. Oh, what an idiot. I see the problem now. I see, friends. See, it's minus 2/18. You with me? There we go. In other words, the 2 is inside the parentheses. This lady the other day, one of my classes, was freaking out. She could not figure out what she did wrong. I'm like, well, you didn't use parentheses correctly. And then she got all mad that I marked her down for not using parentheses. I'm like, kind of matters, man. Kind of matters. Yes, look at that. Look at this. It starts at 0. Bam! At 1, it starts at 0, just like it's supposed to. And then it goes creepy, creepy, creepy on up. Whee! And when it gets here to faux, boom, it's at 100%. Notice it's monotone increasing. That means it never dips down, never turns around and comes back. If it did, that would imply you had negative probability at some point. And that would be no bueno. So we're always gaining probability as time goes on until we get to the end, to the B aspect. Okay, so what I'd like you to see is this. If one were to graph this, I got to stop sharing and start sharing again. He's old. All right, so if one were to graph this CDF, why would I do it here? I was doing it in Desmos. Loser. All right, there we go. So what I'm just going to do is, well, first I'm going to get rid of that stupid thing. I'll keep those, sure. And then I'm not going to keep those. I'll do this. I'm going to go 1 less than x less than faux. And, oh yeah, use your squiggly brackets, Jay. There we go, cool. Okay, and then it's going to be 0. In other words, I had 0 when x was less than, what's going on here? Stop it, go away. X less than 1. And I had 1, always going to have a 100% chance from when x is bigger than 4. Boom, right on there. That's what a CDF will always look like. Always, 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 always. At the far left bound, it'll always be a 0. At the far right bound, it'll always be 100%. From the left bound on to infinity, it's going to be 0. From the right bound all the way to positive infinity, it's going to be 100% always. You can't gain anymore because by the time you got to 4 in this case, we had all the probability there was going to be. There's not going to be. Hey, I found some more. No, you can't because we have it all at this point. Okay. Some will take longer than others to get there. Some will take a heck of a long time. Some will just take a very little amount of time, like in this case, between 1 and 4, bam, that's all there is. It's done. Some will get done quicker. Some will get done, take a lot longer to do. One that we'll see later on is the discrete distribution. Come on, Jay, pull your head out. Is the normal distribution. The normal distribution, of course, you've all seen it. Oh, it's the bell curve, Jay. That's right. This is the PDF. It goes all the way to negative infinity and all the way to positive infinity. Okay. It's the height of women in America. The average 5'5" or whatever it is. That's great. Well, there's no one that's 0 feet tall. That's right. But somewhere over here, like at 3'4" or something, is the smallest woman that's ever been alive as an adult or whatever. From there down, basically 0 chance of it happening. Well, basically anything less than about 4 or 10, there's 0 chance of happening or whatever. So yeah, you see one, you're like, whoa, that was interesting. Yeah, that was weird. It's a little strange, whatever. It happens, obviously, but it's very little chance of it happening. And obviously, there's some gals over here like 6'7" or something. Well, that's very odd. You see when you're like, whoa, that was weird. You don't freak out about it. You just know that's an odd situation. You don't see it every day. From there on out, 7, 8, 9, 12 feet tall, 0, for all intents and purposes. But if you were to draw this, the CDF of this guy would be over here 0, 0, 0, 0, and it would start climbing. It would start climbing. And then, as you can see, like right in here, ooh, it goes really fast, and then it tapers off, and it approaches 1 as it goes out this direction, yes? And in essence, by the time it gets out to here, well, heck, you've got everybody for all intents and purposes, but it's still going to be growing out there. When you look at this, right here, this is where it is the steepest. This is the derivative, if you will, of this guy. And what is this guy at? Well, first of all, the slopes are all positive because the PDF is always greater than 1. That's why this thing is all, well, not true, negative. That's why this thing is always increasing. Okay. Over here, the slopes are very small. That's why it's going up very slowly. And the same thing's true over here. Big slope up here. That's why she goes up pretty fast here in the middle. Okay. It's like a cyclops or something. Okay. That's a big deal. And so then the reason we did this function back here, where did it go? Yes, here we go. The reason we did this function is so we could answer a question like this. What is the probability that x is less than 2? I don't know, whatever. Well, first of all, we know from 0 to 1 is 0. So what we're really interested in is this guy. We're just going to evaluate the CDF at 2. Now, look what you're doing. When you do that, this right here is the answer to the antiderivative, yes? In essence, you're just plugging in that upper bound. That's why a CDF works. You already know the lower bound. In fact, if you were to plug 1 into this guy, if you plugged 1 into here, you know what you'd get? The F of the first bound will always be 0. There's no probability there. And F of the second, of the upper bound, will always be 1. Okay, because by the time you get to the upper bound, 100% has showed up or has been accumulated, if you will. So when you do this, plug this in, you're just going to get, oh, it's too much work. I'll just go back to Desmos and Google it for us here. So when I get over around 2, it is, oh no, my pen's in the way, sorry. At 2, it is 0.22222222222. Bam. Nice. And if I said to you, hey, what's the probability that x is greater than 3? I don't know. But I do know that that plus this is equal to 100%. This I have. This is simply 100%. I'm sorry, this should be the probability of that. So, but this I have is f of 3. So I plug 3 into this guy. When I plug 3 into him, I get 0.555555555555555. And so if I do a little subtraction there, the answer that I seek is simply going to be 1 minus 0.55 repeating, so 0.444 repeating. Nice. And that's going to be a big deal going forward, okay? That idea of a CDF, okay? It's huge. Can't really understate how big of a deal that is. Every important function that we will come across. Continuous-wise, it'll be the exponential, it'll be the normal distribution, it'll be true for the t distribution, chi-squares, f's, all the continuous ones, they'll be exactly like I just did right there. The difference being is that you, oh, all right, Kelly, have a good night. The difference will be is that none of those have an integral in closed form. And so we will use the computer, it will do integrals for us. It'll always start at negative infinity, and it will integrate up to where we tell it to. And it will always tell us the probability that x is less than or equal to the value we asked about. And if I want greater than or equal to, I'll just do 1 minus, and that's how I'll find the value. That's it every single time. With discrete distributions, there are also CDFs, and those guys, well, they look something like this. This thing that Bobby asked about earlier, okay? This, in essence, right here, is your PD. What just happened? PDF, right? That's your PDF column. This, we can make our CDF column. Now you're like, wait, I thought you had to integrate to find CDFs. That's true on a continuous distribution. This is not a continuous distribution. This one, if you recall, is a discrete distribution. Okay, and so because it's a discrete distribution, all I have to ask myself is, when I do this problem here, I want to know the probability that x is less than or equal to the x that we have in question. So probability that x is less than or equal to 0 is just that guy. And then this, well, it'll be equal, oops, it'll be the sum. This is so cool, people. Watch this. It's so exciting. Oh my gosh. Now, watch this. I'm going to put an F4 right there. Oh, bam. Now, watch this. If I did it right. Whee! And so this one should be the first 3. Nice. First 4. Nice. Nice. And so on. And eventually you're going to get out here and it's going to basically be 100%. So by the time we're down around, well, let's be honest, time we're down around 12, we're basically at 100% already. That means that from there to infinity, you add up to a big fat 0.00 or 0.01-ish. Okay. So it's pretty sweet. Basically, you've seen everything there is to see at this point, not a whole lot more to see. And so these discrete ones, you would not graph see exactly. So the computer said, oh, screw it, it's 100%. Okay. You wouldn't graph these necessarily, although a person could. It's not something that we do. I have seen a few books write it this way. Oh, damn it, you can't see that. No one ever says anything. Here, watch me. Let me show you again. All right, this is irritating. Okay, why aren't you showing? There. Okay, so can you all see that now? I'll redo the formula for you. I apologize. I was getting all excited and then, oh, maybe if you push the right keyboard, Jay. It's funny, it won't delete it when you're on the wrong key, on the wrong computer. All right, so this will be my CDF. So this, again, is the one that Bobby asked us about earlier. Oops, I'm sorry, don't equal CDF, just CDF. So this is equal to, probably x is less than or equal to 0. Okay, it's just equal 0. It can't be less than 0. And then the sum of these two guys, but make sure you put an F4 right here. That's going to keep it stuck on F2. so that when I drag in a minute, it's the first 3, it's the first 4, it's the first 5, and so forth. And again, even though I already said this, but you couldn't see it, you get down here around 12, you're already at 99%. Okay, and you keep going, and it doesn't take very long before basically it just says, oh, you know what, forget about it, it's 1. Okay, so by the time you get to 21, the computer's you got 1 minus 0 in essence. So this column is the CDF. That's exactly how we used it earlier too. You want to know the probability that x equals, if you want the probability that x equals 3, then you just read it off of the PDF column, so 0.089. Cool. You want the probability that x is less than or equal to 2, then you just read it right off of the CDF column. It's right here, 0.061, 0.062. Cool, done. You want the probability that x is bigger than 4. Well, then you are going to find 1 minus the probability that x is less than or equal to 4. And so that's going to be equals 1 minus this guy. Remember that 0.28 is the sum from here back. Okay, so it wants greater than 4, so it wants from here down. So I'm going to get rid of these guys and leave them with this much. So basically 72, 71%. Okay. So there will be built-in PDFs and CDFs that will do that for us. I don't have to use Excel every time. This one here is not a defined function. We'll look at Poisson. We'll look at geometrics, negative binomials, binomials. Those are the ones that come to mind. That the computer has built-in functions for both the PDF and the CDF. That's not to say that this one we did here earlier can't work, because obviously we just made one, okay? But the important ones have built-in functions already. Okay. Any questions on that? I think, again, you're right. I think, Robert, it's just a matter of jumping in and playing with it, and then you'll find something that you have a question on. I hope not too much this week. But I don't know what else to say about that. Any questions, comments, concerns? No. All right. Well, I don't have a whole lot else to say tonight. Those are the kind of the things I just want to kind of harp on a little bit. Again, I'm going to do more of that. I'm going to do more asynchronous teaching. That means I put it on a video, and then very little synchronous teaching. I'm just going to talk about some of the important things, some of the more weird things. That's kind of what I want to do in the online time and answering questions. Nothing else. I guess that's all I got for you if there's no other questions.
Hey Jay, I was wondering if you could give me some time after class.
Yes, ma'am. Sure can. All righty. Well, I guess the rest of you want to take off, and Flora, if you want to hang out, yeah, we'll just do that. All right, night, Riggs.
Thank you, Jay. Have a good night.
Take care. Night. Night. Look, they're dropping like flies. Bye. Is it something that's a question, or do you have something that's a little more personal? We can do it offline, a different thing too, if you want, Laura.
No, it's regarding chapter 2.
Okay. Hit me.
So okay, so when I did the homework, I struggled a bit more when it came to figuring out when to use the N and the union and the and and the or.
Hit me. Yeah, let's do it for 3 problems if you want to. You want to?
Yeah.
Yeah. Like which one?
So, for example, when like going over like your lecture, so when it comes to marbled or like dice,
Sure.
and you say, what's the probability of getting a 6 or what's the likelihood of not getting the 6?
So
The way
we're talking
you
on a dice.
Yeah.
Okay, so on a dice, the probability of getting a 6. Okay, well, if it's just getting a 6, oops, then it's just 1 out of 6, right?
Yes.
But so we have to introduce a second thing. So we'll do a dice. What else do you want to do? Throw, roll, flip a coin.
Yeah, sure.
All right. So let's do that. So what's the probability that we roll a 6 and flip a head? Okay, so first things first, is a dice independent of flipping a coin?
No.
Yeah.
Yes.
If you're not sure, ask yourself this question.
Okay.
Oh my God, I rolled a 6. That means I'm totally gonna get ahead. That's ludicrous, right? Because the coin doesn't know or care what the dice did. Is that right?
Yes.
Okay, so they're independent. That's what that means. Okay, so
Okay.
anytime you think of that, independent. Okay. Now, sometimes in life you will have, I have a lot of dependent things. So, hey, for instance, this gal at work, I was working on her car a while back, and holy crap, her tires were completely bald, weather checked, and awful. And I said to her, she's a young kid, and I said, listen, you need new tires. And she's like, well, how much, or when should I get them? I'm like, 2 years ago. These are ridiculous. You are going to kill somebody or yourself, because the chances that she gets in a wreck with tires that are cracked out with big old chunks of missing the sidewall is pretty good. The chances she gets in a wreck with new tires on it's still possible, but it's nowhere near as high. Why? Because it's dependent. Okay. And so that's the kind of thing. A lot of times in our life, we have a lot of dependent things. These are completely independent. So the way the book would write this is roll a 6 and flip a head. Okay. So it's 1 out of 6. Whenever I hear the word and, I'm going to multiply, and that's 1 out of 12. So there's 2 ways to do this problem. There's that way, which I like. That's my personal favorite. Or you could do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Tails, head. There's 12 outcomes here. You see them?
Mm-hmm.
One of them makes me happy. Okay. One of them is what I wanted: a 6 on the dice and a head on the coin. Okay. Now, I don't want to list that all out every time. That's too much work. You with me? I don't want that. So there's a couple ways to do this. That to me is the easy way. So it's 1 out of 6 times 1 out of 12. That's the easiest way to do it. Okay. You could also look at it this way. There's 6 choices for the dice, and there are 2 choices for the coin. That means that it's going to be out of 12 every time. And then you just ask yourself, you visually ask yourself, how many ways can I get a 6 on this sucker and a head on this guy? Well, there's one way to do it. So 1 out of 12. Okay. And that works too. Just in my mind, this one makes sense because I've had that beat in my head that way since, I don't know, 4th grade or whenever we started doing probability. That was like, hey kids, today we're going to flip coins and roll dice. Oh boy. I'm so over that now. It's not even funny, because I don't like, games are fine, I guess. It's just not my thing. And that pretty much goes for all games except basketball or football or something, baseball. But like cards, dice, whatever, I'll play it, but I'm not happy about it. But when people start asking about what's probability of this hand in poker, I don't care. What's probability of, getting a Yahtzee? Well, I could figure that out for you, but I, again, don't care. I play Yahtzee because my kids wanted to play Yahtzee when they're little, not because I was into that. I care about my personal stuff is what's the probability that I'm late for work? What's the probability that this happens, that happens, that this happens in my daily life, right? And so that's going to be mostly based on data, not a ton of this kind of thing. Right. What's another one you wanted to see?
So given this problem, say not only that you want to know when you roll a 6 and when you flip a head, but say you're given a certain amount of tries to do so, would that just be the amount of tries to the power of 1 out of 12? Or would it be 1 out of 12 to the power of number of tries?
So do you want to get a 6? So I guess what you need to ask yourself is what do you want? So if you said, how many rolls will it take before I am 90% confident that this will happen? Stay tuned. That's coming up in a different episode. Okay, that's coming up when we get to discrete distributions. That'll be a negative binomial distribution, or actually, well, technically it's a geometric, but they're kind of kissing cousins. So that is one we'll look at later on. If you want to know what's the probability you get a head or a 6, right? You're going to flip them both, but what's the probability you get either a head or a 6? Well, remember, this is the union.
Which is 1/2 plus 1/6.
So careful now. So how many different ways could I get ahead? Okay. Well, still remember, there's still 12 outcomes total, right? Because there's 2 choices for the dice, or for the coin, 6 for the dice, 2 times 6s. There's still 12 outcomes. But think in your mind, how many different ways could I get ahead? Well, I can get ahead in a 1, ahead in a 2, ahead in a 3, ahead in a 4, ahead in a 5, ahead in a 6. There's 6 ways I could do that, yes?
Yes.
How many ways can I get a 6? I could get ahead in a 6. I could get ahead in a 6, or I could get a tail in a 6. Yes. I'm sorry. How many ways can I get a 6? I could get a 6 in a tail, or a 6 in a head. Yes.
Yeah.
So there's 2 ways to do that. But here's the problem. That's too many. I've miscounted something, right? If you think about this, there's 12 total outcomes. These 6 obviously would make me happy because they have a head in them. Okay. These 2 would make me happy because they both have a 6 in them. But what have I done wrong? I've counted these 6 and these 2. What have I done wrong?
You added them twice?
I added those guys twice, exactly. So I'd have to subtract it off. And that's why we say this is not mutually exclusive. In other words, when you ask for a head or a 6, it's not mutually exclusive because you can get a head and a 6, right? Mutually exclusive means they both can't happen at the same time. You can't be pregnant and not pregnant. You can't be dead and alive at the same time. But you can, in this instance, get a 6 on the dice and a head on the coin. Okay, so we say they're not mutually exclusive. So the formula is always this: the probability of A or B happening is the probability of A plus the probability of B minus the probability of A and B. And again, if you prefer, okay, if you prefer that way, that's cool. Now, these guys are not mutually exclusive, so that's why we subtracted that 1 off of there. Okay, but if there was no overlap, you would just add up the number of the heads and the number of the 6s, and boom, there you go. But in this case, we have, well, that's 8 minus 1 is 7. There's a 7 in 12 chance that we will get either a head or a 6 on the dice.
Okay. Could you give me a dependent case?
A dependent one. Yeah, sure. Let's do one of these numbers. Some marbles or whatever. Nice, whatever. All right, cool. So let's, what's the probability that I get a red one? Oh, I can't do that. It's a Victoria's Secret pink thing written in green. I can't stand it. What's the probability that I get a red one on the second draw, given that I got a black on the first draw? Okay. Now, obviously, what if I got a black and I threw it back in? Then it wouldn't affect the red at all, would it?
No.
So what I'm going to have to do is take it out without replacement. I'm going to eat the M&M one after I pull it out.
Okay.
Okay. So what's the probability I get a red on the second one, given I got a black on the first? Well, let's think about that. So if I got a black one, how many marbles are left in the pot now? Well, there's a total of what? 4, 8, 10, 16 total marbles, yeah?
Mm-hmm.
So if I ate one of the black ones, now there's 15 left, right?
Yes.
And how many reds are there?
4.
So 4 out of 15. That's the answer to that question. In other words, this guy depends on what happened on the first one. Okay, it depends. Well, what did you get in the first one? I got a black. Well, all right. Did you eat it? Yeah. Well, that changed the probability because it's a small population. If this was a swimming pool full of marbles, eat a whole handful. Nobody could tell the difference. There's millions of them in there. It wouldn't make any difference in the probability. But when there's 15, 16 marbles and you eat one of them, well, it makes a big, well, not a big difference, but it makes a difference. And you have to account for it. Sometimes it can make a big difference. It can go from having a chance of happening and then you eat the only purple one. Well, then there's no chance of getting purple anymore. Okay, because you ate it already on the first try. So like, for instance, what's the probability of getting 3 blues on this problem? You can't. There's no 3 blues in there. You ate both of them and then you went for a third one. You can keep drawing all day. There's no more blues. That's it. That's all there is. Okay. So in this case, if I said to you, hey, what's the probability that we get a, let's see here, a black or a green? All right. Let's think about this for a minute. Is there any overlap between black and green? Last time there's an overlap between the 6 and the heads, but this time is there any overlap between, can you be black and green at the same time?
No.
Nope. So this one is just purely what? It's just purely a mutually exclusive scenario. Okay. I'm going to reach in. I'm going to draw one M&M out. There are 16 of those suckers in there because I started with the full 16 again. So there's six black ones. Oh, mute me, will you? That's creeping me out. So there's 6 black ones, and then there's 4, and then there's 4 green ones. So 10 out of 16. Stupid computer. So 10 out of 16 would make me happy. There aren't any that are black and green, so I don't have to worry about pulling one of those ones out, right? I don't have to subtract it off because there's no overlap between black and green.
Yeah. Okay. So I know in the homework there was a lot of combination,
Mm-hmm.
but I still haven't figured out what phrases in like the sentence does it show you that it's supposed to be a combination?
Combination, order doesn't matter. So I can't give you exact specificities, but I know this: on a permutation, order matters. So,
Okay.
so if I am drawing names out of a hat for door prizes, does the position I'm drawn in matter? Well, yeah, I want the trip to Hawaii. If that's the grand prize, I want you to pick me last for the grand prize or whatever, right? If it's you just need some people to come help you and you reach in and grab a handful of 3 names to come help you, well, that's a combination. All you want me to do is haul boxes or something. If it's a race, it's clearly a permutation because order matters. If it's a combination, would be things like, I don't know, for instance, selecting some marbles out of a jar. Well, I don't care which marble I took out of the jar first. It doesn't make any difference. Oh, when I deal you a set of cards, if we're playing cards and I deal you a hand of cards, what's the first thing you do when you put them in your hand? You pick them up off the table. What's the first thing you do to them? If you're like every other person on the planet.
You look at them?
And then you, come on, everybody does it.
Put them in order. I don't know.
Yes, exactly. But they're the same cards. You with me? It doesn't matter what order they were dealt in my hand, because what's the first thing you do? Boop, 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 boop. And when all my jacks are, all my spades on this side and all my hearts on this side or whatever, that's exactly right. It doesn't matter what order they were dealt to you in, because it's the first thing you're going to do is reorganize them in your hand. Does that make sense? That's a combination. Okay. Oh crap! Oh, I was dealt that one on my first hand. Well, you don't care. You're gonna organize them in your hand anyways. It's the difference to that would be if it was a if you're playing what's that poker five what's the Texas Hold'em. Texas Hold'em it does matter what order they're put down, because after, if you see the cards in your hand and you see the one that's the first one that's turned over or whatever, you're like, yeah, I'm gonna bet now because I have a good hand going, or I'm gonna bluff them or whatever. The order in which they pop up matters in that case. And oh, I like that. Nice work, Topher. A pizza, not a padlock for a combination. Very nice. Nice. I like it. Yeah, so a combination lock, exactly. Yeah, so I like that. So pizza, so you get a combination pizza, not a combination lock. Doesn't matter what order they put the toppings on your pizza. That's
Okay.
I like that. I'm stealing it. I'm stealing it. But yeah, that's the game. That's so whenever you just ask yourself every single time, does order matter? If it does, permutation. The order doesn't matter, combination.
So for the test on this is on the 6th week, correct?
What's that?
The test is on the 6th week.
Correct.
Is it going to be similar to the pivot table / the homework, or is there going to be a?
There'll be a pivot table assignment on there. There'll be a pivot table question or two. There will be some probability stuff. There'll be some, like we talked about this evening, with
Mhm.
PDFs and CDFs. There'll be some stuff on there regarding discrete distributions, which we do next week. So yeah, a little this, a little that.
Okay.
I'll give you a review. Well, I could give you a practice test kind of thing ahead of time.
Alrighty, that would help.
Thank you.
Yep.
Well, thank you so much, Jay.
Yep. No problem. Anybody else got a question? I like that though. That's a good one. I like that pizza one. That makes me happy.
No, I'm good.
All right. Well, we'll see y'all later then. Bye.
Have a good night.
You too.